University of Saskatchewan presents Unitel, a program of information, research, and development.
It's springtime in Saskatchewan, and as usual, it's time to unveil the newest innovations in fuel-efficient Supermileage cars. Every year at this time, engineering students at the University of Saskatchewan put the finishing touches on their latest Supermileage creation, readying it for amateur fuel competitions in Oakville, Ontario and Kalamazoo, Michigan. The Shell Canada Fuelathon in Oakville is the first challenge for the university's new entry. It will be trying to beat the world amateur fuel economy record of 2,650 miles per gallon, a record that was set by the University of Saskatchewan team at last year's competitions. Both events are international this year, attracting teams from universities and technical schools across North America. The U of S team has taken first place in the student class at the Shell Fuelathon 3 times since it began designing and building cars 6 years ago, and has even beat the professional teams the last 2 years running. In Michigan, at the Society of Automotive Engineers annual contest, the University of Saskatchewan has always finished in first place. The Supermileage cars bear little resemblance to anything on the road today. Built strictly for competition, they are little more than a housing for the 150-pound driver and the car's small engine. Rick Retzlaff is already an old hand at Supermileage competitions. He holds the amateur world's record as driver of the university's winning car last year, and will be at the controls putting the newest model through its paces this year.
We're usually driving an asphalt track, and it's usually about 2 miles around, and we take 5 laps of the track, so we're usually only traveling about 10 miles throughout the competition. A lot of people think that we actually drive 2,000 miles, to get our 2,000 miles per gallon or whatever, but we don't do that. That would take days.
The car must maintain an average speed of 15 miles per hour as it glides around the oval track. Because the engine is most efficient when the car is accelerating, it is only run in short 5-second bursts. The driver must decide when to start the engine and when to coast to maintain the required average speed.
Basically what you do is you get in and you go around about a 2-mile track, and you're usually traveling about 15 or 20 miles an hour throughout that. So it's not as if you're in any danger of crashing and burning. We use a momentum driving technique, and basically what that is you start the engine up, you accelerate up to about 25 miles an hour, and then you coast. Usually we can coast about a mile and a half with our cars, just from 20 miles an hour. Then you start the engine up and off you go again. So you're continually starting up the engine and coasting.
It's the car's special design that allows it to coast for more than a mile without power. The student designers concentrate on reducing the resistance, both through the wind and along the track, to get their cars to go further on less fuel.
Basically, there's 2 things, aerodynamics and the rolling resistance. The aerodynamics, we use this wind tunnel here that you see to refine the shape of the car so that it's very slippery in the wind. It moves through the wind very easily. The second thing is the rolling resistance, and we use an Olympic track tire that they'd use on a board track for cyclists, pumped up to a very high pressure to allow the car to roll very easily over the ground.
The efficiency of the engine is important too. For the Michigan contest, the rules require the use of a Briggs & Stratton engine, much like the motor that powers the average lawnmower. At the Shell Fuelathon, the students can use a Honda 70cc engine from a small motor scooter. They modify their engines to make them highly efficient, and this, combined with a streamlined design, is a winning combination.
You have to concentrate on all three of the things: engine efficiency, rolling resistance, and aerodynamics. And if you forget one of those, you'll never get anywhere.
But the students never forget. Every year, they must come up with a new design for the competition, and every year they find a way to improve their performance. Many of those improvements are a result of long hours of testing, using scale models and the university's massive wind tunnel. The wind tunnel is one of the largest such facilities in Canada and helps the students perfect the aerodynamics of their cars.
What happens is air moves by here at about 150 miles an hour through this section right here, and we take a model, something like this, a model of the car that we're thinking of building, and we mount it in the airstream and measure the forces on the model. And from those forces we can tell whether the car is very slippery or is, shaped like a brick, shaped like, a car, like a big car.
The wind tunnel helps the students determine the drag coefficient of their cars, a measurement that defines how close the vehicles come to aerodynamic perfection. But wind tunnel testing involves building countless scale models, often only to discover another design idea that doesn't work.
It's a lot of intuition when you get into wind tunnel testing. There's no set pattern. As you can imagine, there's no right way and there's no wrong way. There's just better ways and poorer ways. And so you try to think of, well, what might work? And then you try it, and usually it doesn't. But every so often you'll get that one thing that will work. This is basically a model of our new car, West Wind 9, and we had this in the wind tunnel probably for about 2 weeks straight, testing different configurations and different little add-ons. And that's really where the design starts, is getting a good shape for the aerodynamics.
Once they've defined the best shape for their car, the engineering students must decide how to construct it. This year, they abandoned the usual plastic and aluminum tubing and chose fiberglass to fashion their new car. Everything fits inside the fiberglass shell, even the wheels.
Basically, the big thing we've done this year is put the wheels on the inside of the car. If you notice, this vehicle here has no wheels showing. The wheels are actually inside right there. And that's a departure from what we've done before. And the other big thing that we've done is we've made a fiberglass monocoque car, is what it's called. It's made out of fiberglass, and the skin of the car, the shell, is actually the stressed member. It actually holds the car together. And it makes it lighter and more compact that way.
The new fiberglass car, known as West Wind 9, is only slightly lighter than its predecessors, weighing in at a total of 75 pounds. The fiberglass shell eliminates the need for an internal frame, although an aluminum truss was used to hold the rear wheel and support the engine. Having the wheels inside reduces the drag, an innovation made possible by switching to fiberglass construction.
We thought that it would have better potential for a lighter weight, and we're also very free in the shape of the car that we could make. With mylar and aluminum, you're very limited as to the kind of curves and contours that you can make the car. But with fiberglass, you can make the car any shape you want, anything at all.
Rick drives the West Wind car, but everyone in the student team is involved in getting the vehicles ready for the competitions. Each team is allowed 2 entries in the annual Shell Fuelathon, and this year, the U of S will also take a modified version of last year's winner. Brant Remenda will drive the second car.
This is the cockpit, as it were, and the driver lays in here, feet first, his head up here with crash helmet, plugs himself into here, which acts as the antenna for the radio that he wears in his helmet, so he can talk to the pit crew around the track.
This second car, known as the Phoenix 8, is constructed of steel tubing and a plastic sheeting called mylar. The reflective mylar keeps the sun out of the driver's eyes, but it can still become quite uncomfortable when you're sealed inside.
Well, it's pretty hot and stuffy sometimes. This year we put in a little fan to get the air circulating. This will probably stop the windows from condensating. In previous years we've had trouble with that, trouble seeing out because of condensation on the windows.
The Phoenix looks like last year's entry, but is being improved by lowering it to the ground and adding a more efficient engine. But there are design flaws that make this model consume more fuel than the new fiberglass car.
Well, basically, this is a steel and aluminum and mylar car. The other car is totally fiberglass except for the aluminum subframe at the back that houses the engine. The other car also has the wheels inside, and we found that to be a huge advantage aerodynamically because the wheels contribute about 30% of the drag when they're outside the car, and that can be eliminated by putting them inside.
By modifying their cars every year and trying new, sometimes radical designs, the U of S students have consistently improved their fuel economy records. In some recent events, their closest competitors were more than 2,000 miles per gallon behind them after the final tally.
I think that we have fairly good facilities. We have this wind tunnel that you see here, and we do a lot of our testing in that. We also have a great faculty advisor. I think that makes a big difference, Barry Hertz. And I think we just got a lot of spirit.
The long hours of work on the Supermileage project have paid off at the competitions, but there are also personal rewards.
I feel personally that this is probably as important or more important than any single class that I've taken. And it teaches you how to get something finished. It teaches you how to take something from a design and go through the process and get a finished product out the end. And they never teach you that very much, you know, a continual systems kind of a project. And it's taught me a lot in that respect.
The students work together to perfect their cars, and with sophisticated testing equipment like the wind tunnel, they can predict how the vehicles will perform long before the competitions begin. The cars are usually given a test drive at a local raceway, but most of the precision tests are done in the lab. An inertia dynamometer, which was designed by fourth-year students, simulates the track environment and helps the students run engine efficiency tests on their cars. By the time the spring contests arrive, they've usually got most of the bugs worked out.
We're almost ready to run it. We're just doing some final aesthetic things, like there's a few little sanding to do on the body, and have to make finish the rear body and things like, just little things to get it ready to actually roll. Right now we've had it out on the track, and it performs quite well, it seems. It's really nothing much more major to do. It's structurally ready and race ready sort of thing. Our goal is to get 3,000 miles per gallon. Last year there was 2650 was the world record, so we should make that.
2 weeks later, the team is at the Oakville track, soon to find out how close their optimistic predictions will be. Conditions are perfect for the day's events, and both the Phoenix 8 and the West Wind 9 perform as expected. They finish in first and second place, with the fiberglass West Wind car breaking the university's old world record and finishing with a whopping 2,980 miles per gallon. Faculty advisor Barry Hertz.
We were hoping to get in around the 3,000 mile per gallon range with the new West Wind 9 vehicle, and we did. So we're very pleased with the results.
And your second vehicle?
That was Phoenix, and it got in the mid-2500 range. It was a revised version of one of last year's cars, and it did reasonably well too. It did better than ever before with these new modifications. So it took second place in both competitions, Canada and United States.
And so it's time to begin preparations for the next year. Back to the drawing board in the wind tunnel to create a car that will set another world record by going even further on a gallon of gas.
We'll have something new up our sleeve. We see ways of improving on the west wind design. The frontal area is somewhat larger than it needs to be, plus the engine we used was considerably heavier than it needed to be. So I would look for engine improvements and a smaller frontal area.
This exercise in fuel-efficient automotive design is not all for the glory of being #1 in the world. The university students are using the information they've learned building these competitive vehicles to design a practical roadworthy version of the Supermileage car. Known as Nexus, their car represents the connecting link between the motorcycle and the passenger car. A single-passenger super-light car, Nexus is designed to serve the commuter of the future. It is being built with funding from the federal government.
Yes, we've been working on this project off and on now for about 3 years. It started as a fourth-year design project, then it developed into a master's thesis for Dave Gerwing where the vehicle was designed, and now we're into the construction of the first Nexus prototype, which is actually a contract with Transport Canada. By spring of '86, we hope to have the first Nexus vehicle undergoing preliminary testing.
The three-wheeled Nexus is a study in aerodynamics. Its sleek, narrow cockpit seats one person and encloses the single rear wheel that drives the car. In the front, the two steering wheels sit away from the body in streamlined fairings, giving the car the look of a space-age outrigger canoe. Weighing just over 500 pounds, Nexus is designed to keep up with normal city and highway traffic while using a fraction of the fuel.
And it's designed to carry just a single person. The reason for doing this is studies have shown that 80% of the commuting is really done with just one person in the vehicle. So we've decided to design a vehicle specifically for the task of commuting, driving to work and coming home, that can get up to 200 miles per gallon. So without the energy advantage, a person may as well drive their large van to work every day. But this type of vehicle would probably be able to do the commuting at 1/10 the cost fuel-wise, which we feel is very important. Plus, we want it to be passenger safety compliant, as safe or similar in safety to the typical car out on the road right now. And that's a major task and a major responsibility of our group, to combine the high fuel economy with the safety in this type of vehicle.
A team of 12 engineers, students, and faculty members are working on the first Nexus prototype now. Wind tunnel studies have already helped the designers determine the best overall shape for the car, but there are still many specific design decisions to be made. The wrong shape in a rear-view mirror or a wheel housing can ruin the precision aerodynamics and adversely affect the gas mileage. A sophisticated computer measures the aerodynamic drag of models mounted in the wind tunnel, generating 5,000 separate measurements every second. Even the smallest variations in atmospheric pressure and air temperature can alter the drag coefficient, the yardstick that is the ultimate judge of any new design idea. Design meetings are held regularly, giving the engineers a chance to share ideas and report on the progress of construction. Although others have designed commuter vehicles, the Nexus project is unique. These designers want to create a car that will meet the existing Canadian safety standards for passenger cars.
And the fact is that these vehicles are safety compliant, whereas most of the others built anywhere else in the world of this type are just motorcycle safety compliant, and so they're not really, viable in a sense. In terms of a housewife she wouldn't never think of driving a motorcycle to go shopping, but she'd think of driving something like this. And if she's only got the same safety as on a motorcycle, then you question, how ethical it would be not to provide a passenger type car equivalent safety standard.
And I think if these vehicles started to become largely accepted in the States and there started to be a lot of them around, they'd just instantly change the rules and say that because there is a body enclosure, a person feels that he has some degree of safety, so let's provide it. A person drives much differently on a bike than they do in a car, because they know on a bike their leg is the bumper, and they know in a car that they should at least have some protection. They have that feeling. I think we're headed definitely in the right direction.
Making sure the Nexus car meets the safety standards is the biggest challenge in building the prototype. A special collapsing nose section has been designed to ensure that the car can withstand a 30-mile-per-hour barrier impact. To protect the driver, there may be a 3-sided seat, much like the ones used in Grand Prix racers. And a wraparound bumper, hidden inside the body, will absorb the impact in a broadside collision. The designers are using a wide variety of materials to build a vehicle that is both strong and lightweight.
Yes, it gets us involved in materials that normally aren't used for automobiles. For example, extensive use of aluminum, plastics, foams. We're looking at foam bumpers right now. We're looking at airbag energy absorbing systems and things like that, which are at the sort of leading edge of technology at the present time.
The first Nexus prototype should be finished in 1986, ready for display at Expo 86 in Vancouver. But before the car is even considered for commercial production, it must pass a battery of tests in Transport Canada labs, which could take several years.
Our intention is to demonstrate the viability of this type of vehicle. And we've had a recent request from Transport Canada to plan the analysis phase where we may see up to 10 or so vehicles like this built. You'll appreciate that if a car undergoes a barrier impact test, it's a sacrificial test. So many of the tests that will be done will actually involve destroying totally or partially various of these vehicles. This is a prototype experimental vehicle. It's not designed for sale to the public. They're not available if anyone wants to buy one. They have to come back in quite a considerable length of time. We're simply working on this from a demonstration point of view for Transport Canada.
Right now, there's really no demand in Canada for a super-mileage commuter car. But in the future, there will be. Experts estimate that the world's reserves of oil and gas will run out in less than 40 years if we continue to consume them at the present rate. It seems likely that fossil fuels will remain popular for personal vehicles, so it makes sense to start looking at ways to conserve this precious resource now. Big may be beautiful, but it's small that gets the super mileage.